Now, I think we are ready to apply our applications. I have given enough introduction related to the interface, okay? And you are going to learn even more about the interface when we are going to use the tools to create a model. Now, let me show you the example that I would like to do in this practice, okay? Now, remember, yesterday we have practiced a spreadsheet simulation for an MG1Q, right? Now, today I'm just going to open this weekly questions with solutions file. I am going to skip to the third question, okay? The third question, which is here, okay? If you cannot see my PDF file, my friends, please tell me so. We have an MM1Q, which is a single server queue system with, remember, according to the Canvas notation, this first M means the inter-arrival times are exponentially distributed. The second M here means the service times are also exponentially distributed, and they are independent of the arrival times, inter-arrival times. And this one means that there is only a single server. So this is a very simple queue system where the customers arrive according to a Poisson distribution, which means the arrival frequency follows a Poisson distribution. This means inter-arrival times are exponentially distributed. Secondly, the service times are also exponentially distributed, which is not a very realistic assumption. However, there is a reason for this. We are trying to create the simplest of the models to understand ARENA. So this is going to be a simple model, and the service times are going to be assumed as exponentially distributed. Okay. Now let's read the question. We have a bank. This bank operates from 9 a.m. to 4 p.m. for 7 hours a day, and we assume that there is only one teller, and the client's inter-arrival times are exponentially distributed, with lambda being equal to 0.40 per minute. So remember now, lambda is the arrival rate, which means on the average, 0.40 clients are arriving to our bank. Okay. Remember now, lambda is the rate parameter of both the Poisson distribution and the exponential distribution. And in Poisson distribution, the expected value is also equal to the rate parameter. Therefore, 0.40 here is giving us the average number of clients incoming to the bank in each minute. But that is just an average number. Okay, this is the arrival rate. So the average inter-arrival time, according to the expected value of the exponential distribution, should be 1 over lambda. It should be 1 over lambda, which is 2.5 minutes. Okay, the arrival frequency is this. This means on the average, every 2.5 minutes, a new client is arriving. Now, whenever a client enters and starts the service takes an exponential duration with rate parameter being equal to 0.50. Okay, so remember now, this time, unlikely to the example that we have given yesterday, this time the service time distribution is exponential, and it has the rate parameter equal to 0.50 per minute. Now, this means what? On the average, the teller serves to 0.5 customers per minute, clients per minute on the average. This means the average service time is equal to the multiplicative inverse of mu, the rate parameter, according to the exponential distribution. The average service time is equal to 1 over mu, which is 2 minutes. Okay? So, at every 2.5 minutes approximately, on the average, at every 2.5 minutes, a new client is arriving, and the average service time of a client is 2 minutes. Would you think that the size of the queue will increase infinitely in this case? No, actually it is not. So this system is going to be a steady system. Why? Because the service rate 0.50, the service speed is greater than the arrival rate. Okay. So yesterday when we have concluded the queuing theory chapter, queuing systems chapter, we have mentioned about this MM1 single server queue system, and we have told that if the arrival rate is less than the service rate, then this queue is not going to expand to infinity. So it is going to have a queue which sometimes increases, sometimes decreases, however, oscillates around a steady point. Okay, so we are going to observe a oscillating length of the queue. Okay, the length of the queue will be oscillating, fluctuating. Now, we assume that the service times and the interarrival times are independent from each other. In this question, in part A, it says, use the closed form solutions for the long-run performance metrics of MM1Q to answer the following questions. So remember now, we have told you yesterday, so let me open the presentation file on yesterday. We have told you that under the queuing theory section, we have said that there are some types of simple queue systems. Okay, some types of simple queue systems for which we can determine the exact values of performance metrics by using formulations without using any simulation. And we have also taught that MM1Q is one of these examples. For example, for MM1Qs, if we have the arrival rate less than the service rate, in that case, the server utilization, the average number of clients in the system, or the average waiting time in the system, or the average waiting time in the queue, or the average number of clients in the queue, all these performance metrics can be computed by these formulations. Now let me repeat once again. These formulations can only be used for MM1 queues, okay? Where we have exponential interarrival times and independent exponential service times, and we only have a single server. In other type of queues, these formulas are not valid. Do not use these formulations for other type of queues. And as I have forgotten about this slide, the last slide. There are other type of queue models like MMC. What is MMC? It's a interarrival times exponentially distributed and service times are exponentially distributed. And what is this C here? The number of parallel servers is C. There are C multiple servers parallel to each other serving to these queue. And for MG1 queues or MG infinity queues or MMCN queues, so you can read the details of these by looking at the candles notation. For example, what is MMCKK? Interarrival times are exponentially distributed. The service times are also exponentially distributed. There are C multiple servers. The system capacity is K. So only K clients are allowed in this queue. If the length of the queue is equal to capital K, then a new client cannot enter the system. And here the second K is the size of the calling population. The size of the calling population is also K. I mean, if the size of the calling population is equal to K, so remember, what is the calling population? It is the number of potential clients who are outside the system who can enter the queue, right? So if the calling population size is equal to K, then the capacity automatically will not be violated, right? It is not going to be violated in any way because at most K clients can enter the system from the outside of the system. Therefore, this capacity constraint will not be violated in any way. Okay. So these are the queue. I mean, why I have explained these. These are the simple queue models for which the queue theorists can generate closed form performance metric formulas, just like in the MM1 queue. So we do not need to make a simulation, run a simulation of these queues because the closed form performance metrics can be calculated by formulations. However, this is not the part of this course. In this course, I only provide the closed form performance metrics for MM1 queues. And why I have done that? Because now in the second hour today, I am going to create a simulation model of the MM1 queue. And while I create the simulation model of MM1 queue, I am going to compare my performance results in the simulation with actual theoretical performance metrics obtained with these formulations. So I will see if my simulation results are actually true or not. Okay? So I will see if simulation is a reliable technique or not by looking at these true performance metrics. And these performance metrics can be calculated by using those formulas as here. So in this MM1 single server queue system I have just described with inter-arrival rate being 0.40 per minute and the service rate being 0.50 per minute according to the exponential distribution, and where we have a single server, the average queue waiting time is 8 minutes. The average time spent in the system is 10 minutes. The server utilization rate, the fraction of time where the server is busy will be 0.8, which means in 80% of time. So in 80% of time, the server is going to be busy. We have capital L here, which is the average number of clients in the system. In the long run, on the average, we observe 4 clients in the system. And LQ, capital LQ here, is the average, in the long run, the average length of the queue, which is 3.2 clients. Okay? Now we are going to compare the simulation results and if they are consistent with these values. So let me show you that now if we are going to create a simulation project of this simple model, okay, simple system, first we need to define the project itself, right? Remember, we need to name the project. We need to put a name to this project. And here under run, okay, under run, we have setup. Okay, under run here we have setup, and when you click on the setup, you will see a tab that is called project description or the project parameters. Okay, so in the new version it is called project parameters. In the old version it is called project description. So we have project parameters here. So I need to put a name to my project. So the name is going to be this, MM1 Q system. Okay, that is the name of my project. Why I do this? Because I mean, if somebody who would like to learn about this model and what it describes can check this project description from here, and I write my name. My analyst name is İsmail, for example. So anybody can see that this project is prepared or updated by İsmail. Okay, when they check the file, and I explain the project description. This project simulates an MM1 queue system and estimates general performance metrics. Okay, so we write a description here. And other than that, we have statistics collection here. So it says, so we have entities, resources, and queues, clicks. Okay, we have ticks on them, and for the others, we do not have ticks. So this means what? In the end of the simulation, the arena is going to report statistics related to entities, resources, and queues. Okay, and it is not going to report any statistics related on costing, tanks, stations, transporters, conveyors, activity areas, or processes. Okay, so I am just going to click on processes as well because I would like to get statistics on the processes as well. So this means by default, Arena is going to give us the default statistics related to entities, resources, queues, and processes. So what are the entities here? In this simulation model, the entities are the clients, right? That's queue in the queuing system, simple queuing system. The entities are the clients who enter the queue to get a service and then depart from the system when their service ends. What are the resources? The resources are the resources that we use in the server. So for example, the server itself is a resource. Okay, the server itself is a resource. And we have queues. So we have a single queue in this system. And we have a process. Okay. So you are going to see all of them in this MM1 queue. So I click OK on that. I click OK on that. And I have created its name. Now, if I do not want to lose my model, for the first time, I need to save it. So I say, save this model. And the name of the model is going to be, let's just say, let me save it to the desktop. Okay. And in the desktop, I will open a folder which is called MM1Q. And I'm going to save this model as MM1Q in my desktop. And you see the save file has the DOE expansion, DOE. Okay. So DOE means what? Design of experiments. Design of experiments. Because of that reason, because in simulation, we are actually making an experimental design. We are trying to experiment different policies under a simulation model. So because of that reason, they choose the extension of DOE, design of experiments, when they create their model. So the default file type when you create a model is going to be DOE, which can be opened by Arena software. Okay. Now let's click on that. So we have saved our model for the first time. Now I am going to use basic process panel and I am going to create entities. Okay. So I have checked this create file, create module from the basic process panel. And this create module is going to help me to create entities. Okay. First of all, I double click on them. Okay, let me show you again. I double click on the create model. Then I see a window. And this window is the dialog box. It is called the dialog box of the create module. Okay. So I change the name of the create module. I say that arrival of clients. Arrival of clients. Now, the name of the module is going to be this. Okay, what I am going to see on the top of this module is arrival of clients to understand it better. Now, what arrives? What are the entities in the system? A client is an entity, right? So when I create entities with this create module, the entity that I am going to create is going to be the client entity. So the name of the entities are clients. And because this is a create module, automatically the create module is asking me, what is the time between arrivals? So choose the time between arrivals. Now in this question, remember, the time between arrivals is exponentially distributed, right? Expo. So there are several options here. You can choose exponential inter-arrival times. You can create arrivals based on a schedule. You can create arrivals with constant inter-arrival times, which means at periodic time points, the arrivals are occurring. And you can also choose to write an expression. And if you choose to write an expression, you can choose other distributions as well. So, but by default, exponential distribution is here. But my friends, please be careful here. Unfortunately, in Arena, we are not using the arrival rate as the parameter. Instead, we write the average inter-arrival time, which is 2.5 minutes. Remember, in the question, the arrival rate is 0.40 per minute. However, in Arena, when we write the exponential distributions value, we write the average inter-arrival time, which is 2.5 minutes. Okay, and we need to change the unit to minutes from here. Okay. Now, at every arrival, only one client will arrive. They are not going to arrive in groups. Okay. For example, they are not going to arrive in 3 people. At every arrival, only 1 people will arrive. Okay. So entities per arrival is 1, and the maximum arrivals is infinite. This means the simulation is not going to stop unless we stop it. So if you say, for example, the maximum number of arrivals is 100, then the simulation is going to terminate when 100 clients arrive. So another client will not arrive. This is 100 client is going to be the last client that arrives. Okay. And therefore I say infinite. Okay. Maximum number of arrivals is infinite. And the first creation, it says. So when does the first client arrive? When does the first client arrive? Does this first client arrive at time 0? No, let's just say we are going to assume that the arrival time of the first client is also going to be exponentially distributed with 2.5, with average 2.5. So I am going to write a comment here, okay? A comment here, which represents the exponential random variate with average 2.5, but I do not know that comment. So what I am going to do is this. I am going to right click on here, and I will say build expression. Now, again, I am going to check the random distributions here, and I am going to look for exponential distribution, and it asks me, what is the mean of the exponential distribution? I say 2.5. I say 2.5, and it gives me the comment, expo 2.5. Okay? So I click on OK. Now here's the question, my friends. I have told that here, these inter-arrival times are exponentially distributed with 2.5 minutes here, but I write expo 2.5 here, but it does not understand anything that it is going to be related with minutes. So it only understands it is going to be 2.5, the average. But is it going to be minutes or hours or seconds? So I haven't introduced anything here. Now I am going to show you this for the first time. So let's click on OK. Let's click on OK. So we have created an arrival process here. So the create module here creates the arrival processes. Now, my friends, under the run here, under the run and setup. So this is the point where we have defined the project parameters, right? Project parameters. Under the replication parameters tab, which is the top left corner, which is at the top left corner at the moment, replication parameters, it says, what is your base time units here? In this simulation, what is your base time units here? Which means if you write a time without defining its units, automatically the unit of that time is going to be counted as minutes. So I choose my base time units as minutes. So everything that I define numerically as a time is going to be defined in minutes. Okay? This means in my whole simulation, I am going to work with minute units. This is my base time unit here. So I click on OK at the moment. So it has saved it. Anything that I'm going to create is going to be created in minute units. Okay. So if I double click on this first arrival time of the first client will be exponentially distributed with average 2.5. Okay. So I have created the arrival module, okay? Now, you see in the spreadsheet module, under this page, in the spreadsheet module, my friends, maybe I can, sorry for that, but maybe I can increase the resolution size, okay? So let me try to increase the resolution a little more. I think this is as better as you can get, as best as you can get as the resolution. So, okay. So you see in the spreadsheet view, when you click on a create module, you see the details related to create module. Okay. So the name is arrival of clients. The entity that we create is a client. The inter-arrival time distribution, the type is random, exponential, with 2.5 minutes average. And at every arrival, one client is arriving. And the maximum number of arrivals is infinite. And the first creation, again, is exponentially distributed with 2.5 minutes. Okay, so this is the spreadsheet view. Instead of clicking on it and changing everything in the dialog box, you can change everything also on this spreadsheet view if you are professional enough. And there is another thing. Now, you see max arrivals here, right? Max arrivals. And you do not understand what it is. It says max arrivals, but I do not understand what it means. So there is a question mark here. Click on that and hover your mouse over the max arrivals here. Okay, hover your mouse here and click on that. Okay, maximum number of arrivals that this module will generate. When this value is reached, the creation of new arrivals by this module ceases. Okay, and the valid entry is expression. You can write an expression that it says. Okay, and now we have a data module here. We have created an entity, right? So this create module in the flowchart creates entities. This means we have created an entity. When you create the client entity with the create module, automatically in the spreadsheet view of the entity here, remember now we have two types of modules in the basic process. One of the types is the spreadsheet module, and there is a spreadsheet module that belongs to entities. So when you click on entity here, my friends, you see in the spreadsheet, we have an entity that is created, which is named as client. Okay. Now in the animations, you are going to see these entities with pictures as reports. Okay. So we are going to see report pictures. So let's just say, instead of report picture, I want to see woman pictures. Okay. Woman pictures. So I am going to see woman when the entities move in this queuing system. Okay. So picture of woman. And there are other type of costs that you can introduce here. For example, as entities move towards the system, they can create costs or they can create profits. Okay. You can write these costs, holding costs, for example, for each minute that these entities spend in the system, there is a cost is created. So that is called the holding cost. Okay. I'm not going to explain the details of this cost because, you know these costing structures from a cost accounting actually, and you can learn about this in inventory management or manufacturing planning course. In this course, we are just going to focus on the performance metrics of queuing systems. So as you can see at here, I have changed the picture of the entity to a woman. Okay. So from the entity spreadsheet module here, you can change the pictures and other parameters related to a client, or you can simply double click on that. If you double click on that, you will see a dialog box and you can change everything through the dialog box as well. Okay. Not just in this stupid spreadsheet view. If you double click on that row, you can also turn on a dialog box and you can change everything. Again, you can ask questions. So what does that mean? You can ask questions to understand them.